Welcome to this class. So in this class, we'll discuss about partial differentiation. Okay, so first we'll discuss about what is the meaning of partial differentiation. So we know the differentiation term previously. So let's discuss by analogy. So let us say we have one function where this value of y depends on the value of x. So we can write the dependence of y on x through some function which we usually write as y as f of x. So what it means here? So the value of y basically depends on value of x. So here we call this x as independent variable. This is independent variable. And of course, y depends on x. That's why through this function form, we call this variable y as a dependent variable. Dependent variable. And we know the basic definition of differentiation or derivative. Suppose if I perturb or change the value of x by small value delta x, so what does that mean? Suppose if I change x to some value x plus h, where this h is tending to 0. So if I perturb the value of x by small amount h, almost tending to 0, then y is going to change. And the rate of change of y with respect to x is called its derivative, what we usually write as dy by dx. Dy by dx is equal to limit as h tending to 0 function f of function value at x plus h minus function's value at x itself. So this is basically y at x plus h minus y at x. So this is the value difference in y with respect to difference in x, because we perturb value of x from x to x plus h by small quantity h. That's why its limit is tending to 0. So this is how we define the derivative of single variable function. Means like y is only dependent on the variable x. So what is meant by partial derivative now? Now suppose let us assume that there is a variable z whose value depends on two different variables x and y. So dependent of this variable z is written through function from form as f of x comma y. So what it means actually? So the value of z basically depends on value of x as well as value of y. So here we call these variables x and y to be independent. So these are the independent variables here. And of course, z depends on x and y. So we'll call this as dependent variable. So now here, compare these two forms. So on the right hand side, we had only one independent variable, right? And the value of y depends only on x. So if I perturb the value of x or slightly change the value of x, then it is going to change the value of y as well. But here we have two independent variables. So we have a choice here. So either you can perturb x or y, or you can perturb even both. But it is not necessary that to change the value of z, you need to change both. Even if you change either x or y, then also the value of z is going to change, right? So it means that z depends on x and y, and they have their own dependability. So they have their own dependability. So z independently depends on some variable x and the other variable y, and they have some different forms, the dependence. So that's why, suppose if I perturb the value of x, then z is going to change. If I perturb the value of y, then also z is going to change. So I can write the rate of change of z with respect to x separately and with respect to y separately. So that is what we called a partial derivative. So I am going to write this partial derivative. So let me write here. So rate of change of z with respect to x is partial derivative. Here we called as derivative because we had only one independent variable x. So here we had two. That's why I can define the rate of change of z either with respect to x or with respect to y. And if I find the rate with respect to x, then I'm going to call this as a partial derivative of z with respect to x, and is denoted by I'm going to write this as this. This is nabla del z by del x. You can pronounce this as del z by del x, or sometimes daba. You can, somebody may use daba z by daba x, nabla z by nabla, depends. But usually I prefer to use del z by del x. And how we define this? So let us define this. So this del z upon del x is again, see, so we are going to use the same analogy. Here we are differentiating with respect to x, so we perturb the value of x. Here we are finding partial derivative with respect to x, so I am going to take a limit again h perturbed with a small amount which is tending to 0. So again this functional form f, so I'm going to write this f as I perturbed x, so I am going to write x plus h, keeping y constant. This is very important. So as I am finding the rate of change of z with respect to x, I'm going to perturb only x values and not y values. So I'm going to keep the y values to be constant, minus f of x comma y divided by perturbation in x, which is h. And this h is tending to 0. Sometimes this can be also denoted as f as a function form, and we use a suffix to represent the derivative with respect to which independent variable. So as we have found this with respect to x, so I'm going to write x at the suffix of f. This is how, or you can sometimes write as del f by del x. That is also fine. So here as you write df by dx, you write here del f by del x. On the same note, you can define the derivative with respect to y as well. So how do you define that? So this is how you define that. Del z over del y is limit, suppose I perturb by some different amount, again which is tending to 0, but as now I'm going to differentiate with respect to y, I have to keep this x variable constant. So x comma y perturb by small amount k minus f of x comma y divided by k, which is perturbation in y. So this is how we define partial derivative, and these derivatives we call is partial derivative. So here the origin of partial derivative is multivariable function. Variable function. So what is multivariable function? Here our function f, it depends on the values of x and y. So we have multiple independent variables. So we have multiple means more than one, multiple independent variables, and that's why we call this function as multivariable function, in which the value of z depends on both values of x and y. So in this, as this z depends on both, I can define the rate of change of this function with respect to these independent variables separately, which we call partial derivative. And this is how we exactly define them, exactly similar to what we have defined for single variable function, which is y equal to f of x. So these are the basic definitions. And now we are going to use this definition to find out the partial derivatives and see through examples how to find those partial derivatives quickly. So again, just to remind, z, our function form was like z as a function of x and y. We have defined this del z over del x as limit h tending to 0, f of x plus h comma y minus f of x divided by h. And at the same time, we had another independent variable. So we defined partial derivative of z with respect to y as a limit. This now k tending to 0, f now perturb y by small amount k minus f of x comma y, sorry for this, x comma y divided by k, divided by k. So this is how we define the partial derivatives. All right. So these are the definitions of partial derivatives. Now, what is important here? So while defining this, note that while defining del z over del x. So basically we are differentiating this function z with respect to x. We took y to be constant. This is very important. So what it means actually, now you are finding the rate of change of z with respect to x. So all other independent variables should be considered to be constant. So suppose if I had here f of x, y, and z, and suppose if I write w as a function of x, y, z, function of x, y, z. So I have three independent variables. So at a time, if I want to define del w by del x, for defining this, I will consider y and z to be constant. Suppose if I want to define del w by del y, at that time, the other two independent variables x and z to be constant, and so on. So here we only considered two independent variables. So while defining this del z by del x, I'm going to assume the other independent variable to remain constant. And here, while defining del z over del y, we took the other independent variable x to be constant. So if you want to define del z by del y, simply consider x to be constant. If you want to define del z by del x, y to be constant. So I'm going to generalize this and write like this. So note this. So let us note this. Suppose if we have a dependence of function, so let us write y as a function of x1, x2, x3 dot and xn. So we have n independent variables, namely x1, x2, x3, so on up to xn, and only one dependent variable through this function form, one dependent variable, which is our y. Now, suppose if I want to calculate del y, I can define the rate of change of y with respect to each independent variable separately. So first of all, I will write del y by del x1. So while defining this, consider other variables. Other means x2, x3, x4, and so on up to xn to be constant. So in general, if you want to differentiate your dependent variable y with respect to del xi, consider the remaining variables. So remaining means, let me write xj. Remaining, consider xj where j is not equal to I, because here if you see, you are differentiating with respect to x1. So other than x1, you have considered all other to be constant. So similarly, if you are differentiating with respect to I, the remaining one xj where j is not equal to I are constant. These are considered to be constant. So this is the basic definition and basic note to keep in mind while differentiating these multivariable functions. All right, so let us see through examples how we can go and find out the derivative through basic first principle, what we say, and directly as well. So I'm initially, to make you comfortable, I'm going to use the first principle, the basic definition through limit. So let us take an example. Suppose if I consider z as a function of xy, so let me write as z as a function of xy to be equal to xy, and now I want to find out del z over del x and del z over del y. So first of all, I'm going to write through basic definitions. First principles, del z over del x equal to limit h tending to 0. So let me write as this functional form. Let me denote this function. We can write this as function from x comma y to z. So let me use that function notation f only. So f of x plus h comma y minus f of x comma y divided by h. So what is, so let me write here now, f of x comma y is equal to xy. Therefore, f of x plus h comma y. So instead of x, you need to put x plus h here. So this would become x plus h multiplied by y. So this is xy plus hy. This is xy plus hy. So if I use this here, this is xy plus hy minus f of x comma y is xy. This is xy. So xy gets cancelled, divided by h, and taking limit h tending to 0. So what we get? H gets cancelled. So we end up with having only y. So I can now define as del z over del x is equal to y, And this you can directly figure out from this expression itself. So remember the note. If you want to differentiate with respect to x, all other independent variables are constant. So while defining del z by del x, our other independent variable y is considered to be constant. So if you consider this function in which this y is some constant and you are differentiating with respect to x, so derivative of x, so del z, so this is how you define del z by del x is equal to del over del x of xy. And while defining or differentiating with respect to x, you consider y to be constant. So you can take this y out, and now you can find the derivative of x with respect to x, which is obviously 1. And you find the answer to be equal to y, which is the same case by using first principle. So similarly, now I'm going to find del z by del y. So again, by the definition, limit k tending to 0, f of x comma y plus k minus f of xy divided by k, which is equal to, again, limit k tending to 0. Now let us find f of x comma y plus k. So instead of y, you now put y plus k. So this is x into bracket y plus k. This is what? xy plus kx. Put it here, xy plus kx, and minus f of x comma y is xy. Again, xy gets cancelled. Denominator is k. Limit k tending to 0 gets cancelled, equal to x. And again, by the definition, if you by remembering the note, del z by del y is equal to del by del y of xy. So if you are differentiating with respect to y, you now consider x to remain constant, take it out, x del over del y of y, which is equal to 1, and you ultimately get an answer equal to x, which is the same case what we got from first principle. So in this example, I have shown you both approaches, but as we'll be going into detailed vigor, we'll be following the second method, in which we'll be directly using or differentiating with respect to particular independent variable. And while doing that, we'll consider other independent variables to be constant. Okay, all right. Now, similarly, as we have defined this function, so let me write this again, z as a function of x comma y. Now we have defined first derivatives. So we have defined first derivatives. What are the first derivatives? You can either define rate of change of z with respect to x, or you can similarly define with respect to y. These are the first derivative. Now you can also find the second derivatives also, as what we did derivatives, as what we did in our single variable function. So now I have again two choices, because in single variable function, y equal to f of x. So I can define the first derivative equal to dy by dx. Second derivative, again, derivative of dy by dx with respect to x, which is equal to, we usually write d2y upon dx2. And so on. You can continue till nth derivative if it exists, right? So, but in multivariable functions, I mean to say, in which the number of independent variables are more than one, we always have a choices of the variable with respect to which we have to differentiate. So to get the second derivative, I need to differentiate the first derivative. But again, in that also I have two options, whether to differentiate this del z by del x or whether to differentiate this. So again, so that is how we define. Suppose if I differentiate this del z by del x, Now again for this also I have two options, whether to differentiate with respect to x or to differentiate with respect to y, del z over del x. So now I have differentiated del z by del x, but once with respect to x and once with respect to y. So I write this as d2z upon del x del x. You can write del x square. And here d2z, second derivative, that's why d2z, del 2z, sorry, not d2z, sorry for this, del y del x. So this sequence is important, del y del x. On the similar note, if I start from here, I can differentiate this del z by del y. Again, I have two choices, either to differentiate with respect to x, or I can also differentiate with respect to y, del z over del y. So here, what I get, del 2z over sequence del x del y, and here what we get, del 2z over del y square. So I have four different terms for the second derivative of this function z, in which I can define the second derivative of z with respect to x, second partial derivative of z with respect to x and y, second partial derivative of z with respect to y and x, and second partial derivative of z with respect to y. So this is how we can define second derivative in case of multivariable function. Okay, so what is interesting here? So these two terms, suppose your function is continuous with respect to x and y values, then these two forms are equal. So what I mean to say here is del 2z over del y del x is equal to del 2z over del x del y. So this is very important. So what I mean to say actually, so what I mean to say is here the sequence of differentiation is not important. So here I am taking the derivative with respect to x first, and then I am differentiating with respect to y. So sequence is like here first x, then y. And in right hand side, the first I am differentiating with respect to y, and then I'm going to differentiate with respect to x. So here first y and then x. But what I say here, I am saying that both are equal. So both are equal means whether you differentiate with respect to x first or y first, your results would be same. So the sequence of differentiation is not important unless you are ultimately differentiating for the same number of times. So here see, if we are differentiating this z function with respect to x once, with respect to y once, with respect to y once, then it is fine. Sequence is not important given the condition that your function is continuous with respect to x and y. So this is very important, and which will be understanding through the example itself. Okay, let us take an example. Some kind of you can take any kind of example. So let me take an example. Z equal to x square y plus xy square plus x square y square. So let me differentiate with respect to x first. So del z over del x. So remember, you are now differentiating with respect to x. So you must treat your other independent variable y to be constant. Okay, let's do that. So first term, y constant. So derivative of x square is 2x. So I get 2xy. Okay, plus second term, again y constant. So y square is constant. Derivative of x is 1. So I get only y square. Plus again y constant, y square constant. Again derivative of x square 2x. So this is 2x y square. Now let us differentiate del z. Let us find del z by del y as well. Now what we'll do here, now we are differentiating with respect to y. So let us consider x to be constant. So x square is constant, derivative of y is 1. So I get here x square. Plus, fine, x constant, y square, derivative of y square with respect to y is 2y. So I get 2xy. Okay, plus again x constant, x square constant, derivative of y square is 2y. So I get 2x square y, 2x square y. Now I'm going to differentiate this. So I'll write it here. Differentiate this with respect to y, with respect to y. And let's differentiate this with respect to x, and let us see if we get the same answer or not. So what I'm going to do here, differentiating with respect to y means del by del y of del z by del x. So I can first step, I'll write it in detail. Del by del y of 2xy plus y square plus 2xy square. All right. And same time I'll write it here as well. Del by del x of del z over del y equal to del by del x of, this is x square plus 2xy plus 2x square y. All right, no problem. Let's do this. So what is this notation on the left hand side? So this is second derivative, partial derivative of z sequence del y del x, because you have differentiated with respect to x first. Okay, differentiate with respect to y. So I'm going to assume x to be constant. So x constant, derivative of y is 1. So I get 2x plus, again with respect to y, 2y plus y square, derivative of y square with respect to y, 2y into 2x. So this is 4xy. All right. So here, what is this notation? Second derivative, second partial derivative of z with respect to now x and y. Now here we have differentiated with respect to y first and then with respect to x. All right. Right hand side differentiated with respect to x. So x is constant. So sorry, y is constant. Derivative of x square with respect to x, 2x plus y constant. Derivative of this is 2y plus y constant, x square derivative 2x. So you'll get 4xy. 4xy. So look at these two terms here. 2x, right hand side, 2x, 2y, 4xy. 2x, 2y, 4xy. So what it means here, del 2z over del y del x is equal to del 2z over del x del y. So if your function is continuous, because this is kind of polynomial function in x and y, so this must be continuous over the range of real numbers. So in such case, your second partial derivative with respect to x and y, irrespective of the sequence in which you have differentiated, will not cause any error. Both would be same. So these are the, this is the beautiful result about partial derivative. And similarly, you can carry out more examples to see this result. And at the same time, you can definitely find out the second derivative del 2z over del x2 just to exercise. If you differentiate this with respect to x, you can get this as 2y plus 2y square. And if you differentiate this with respect to y again, you get second partial derivative of z with respect to y. And if while differentiating with respect to y, consider x constant. So this is 2x. This is 2x plus, sorry, 2x square. 2x square. So these are the second derivatives of z with respect to x and y. But to note here, this is very important. So this is how we define the partial derivative terms. So let me brief about partial derivative again once more. So we had a multivariable function z, and which function form is defined as f of x comma y to start with. Actually, you can have n number of independent variables. That is also fine. Now we have to define this del z over del x. Similarly, you can find del z over del y. Basically, rate of change of dependent variable with respect to any independent variable. You can define it separately. So while defining this, you assume y to be constant. Not exactly like assumption. There is nothing like assumption in mathematics. Assume in the sense that consider this y to be constant while doing this treatment. And while doing this treatment, del z by del y, take, let me write, take x to be constant. So this is how we define, because we are studying the dependence of z on y. So we cannot perturb x at the same time, right? So in this case, we are studying the dependence of z on x. So at the same time, we cannot perturb y. So this is not the case, right? So this is how we defined it. And to find out the del z partial derivatives, first derivatives, we have remembered this particular thing. If you are differentiating with respect to x, take other independent variables to be constant, differentiate it, usual practice. So whatever be the function, do the similar strategy and you'll be through, right? In this lecture, we have discussed about the partial derivative, the definitions of partial derivative, and second partial derivatives with respect to x, y, their sequence, dependability on sequence or not. We have discussed all these things. So in the next class, we'll discuss about what if we have multiple functions and we have multiple independent and dependent variables as well, and how to differentiate, how to write the partial derivatives, how to write the total derivatives, and so on in details.